Hello everyone, good morning. My name is Nirnimesh Ghosh and I am a PhD candidate at University of Arizona. And this is the work I have done in collaboration with my advisor, Dr. Lazos and Dr. Lee. It's about device bootstrapping, which is resistant to signal manipulation attacks on the physical layer. In several applications, a group of devices need to be deployed either simultaneously or in a sequence of very short time. For example, in the unmanned aerial vehicle swarm, multiple UAVs need connected to a central controller required to be deployed at the same time. In body area network, a user may initiate variables which are connected to a centralized hub, and this is done in sequentially in very short time. Or in a battlefield scenario, a group of soldiers who are deployed in an ad hoc team, they connect to each other and they have to be deployed simultaneously. In all these applications, the data which is exchanged between the members of the group are very important and sensitive. So trust establishment between the devices is required when the group is deployed in the starting. So the trust establishment in a group setting, in this example, D1, D2, and D3 wants to establish trust with A. This can be done in two different ways. In first, either a group trust establishment protocol can be run, or a pairwise trust establishment protocol can be run between each device and the hub. And in process, this can be extended to the trust establishment in the whole group. In our work, we look into the scenario in which multiple devices, they connect to a central hub. So we look into the secure pair of group devices to the hub. And by the end of this device pairing, each device will have achieved mutual authentication with the hub, or each device and the hub will share a common key. Let's look at the existing solutions for pairwise trust establishment, where D is trying to securely pair with a device D is trying to securely pair with the hub A. In the secrets-based methods, a user can manually enter a password to the device and the hub. However, in this case, some of the new devices, such as the wearables, do not have an interface for the user to enter password, so this can become difficult. Or alternatively, manufacturers tend to preload a key to each device when they are shipped from their manufacturing process. But in this case, sometimes the default keys tend to get leaked, and the users don't tend to change these default keys, which could lead to compromise of devices. Alternatively, there are some secret-free solutions, such as the device D and A can exchange, do a Diffie-Hellman key exchange, but it's known that due to missing authentication of these key primitives, it's vulnerable to man-in-the-middle attack. So to improve the security, researchers have proposed to use out-of-band verification to do authentication and use modalities such as light, sounds, etc. But in this case, they require advanced interfaces. There are also solutions to derive keys from the ambient environment, which is done by D and A simultaneously. These are the context-based verification techniques, but these also require multiple sensor modalities. Therefore, in this work, we focus on in-band verification technique, which only require a common radio interface, which is available in all the wireless devices. But the main problem in extending a secure peering protocol to a group setting is that the success probability for an adversary increases with the increasing group size. In this plot, we show the success probability for an adversary for breaching any pair in the group versus the group size n. And for this, we fixed the probability of probability of breaching for the adversary for a single pair to PS. And from this graph, we can observe that the success for the adversary increases exponentially with increasing number of groups. So in this work, we asked the question, can we use the number of devices in the group to improve the security of this peering process in a group setting? So the threat model we use for this work is a group of devices, for example, D1, D2, and D3, want to establish pairwise trust with A. And the adversary is also attempting to establish pairwise trust with A. Because these devices and the hub do not have any pre-shared secrets, A cannot differentiate between the adversary and a device. Therefore, the adversary can attempt to join the group as an extra member. However, this problem can be easily solved by fixing the number of group members such that the adversary is now prevented to join as an extra member. So the adversary will be forced to hijack a legitimate peering session, in this case of D3, to join as a legitimate device to A. The adversary can achieve this by performing man-in-the-middle attack over wireless. And in our threat model, the adversary can join A as a legitimate device, or it can join to the device as a rogue hub. So to perform man-in-the-middle attack over wireless, in the worst case adversary, we assume the adversary has knowledge of all the physical layer characteristics of the wireless channel between all parties. It can synchronize to the transmission of different devices by listening to the preambles, and the adversary can perform overshadowing or signal cancellation attack. So let's see how the man-in-the-middle attack over wireless can take place. In this example, D is transmitting a message such that the signal RD is received at A. And the adversary is attempting to inject its own message such that RM is received at A instead of RD. This can be done easily by an overshadowing attack where the adversary transmits at a higher power. So at A, RM is detected instead of RD. This problem can be made hard by transmitting the message from D in on-off keyed modulation. In on-off keyed modulation, the messages are Manchester coded such that bit 1 is realized by on and off slot, and bit 0 is realized by off and on slot. And to transmit an on slot, energy is injected by the device into the wireless channel, and to transmit an off slot, it's just absence of energy. So now for the adversary to change RD to RM, it will have to annihilate energy from the wireless channel to flip a bit from 0 to 1 or 1 to 0. And this can be done if M injects a signal such that RM is of opposite phase of RD. But since to inject energy, D transmits random signals, therefore the adversary cannot know these signals in advance. So to perform this attack, adversary will have to receive the signal from D and inject a signal such that RM is received at opposite phase of RD. This can be done if the adversary can achieve this if the path through the adversary The indirect path through the adversary and the direct path have a path difference which is the odd multiple of wavelength over 2. And for these, all the possible locations will lie on this ellipse. And multiple number of these ellipses are possible, but it's bounded by the delay of the indirect path such that the signal cancellation takes place. Now, extending this to a two transmitter, here the adversary will be placed at the intersection point of the both transmitters, both receivers, such that the adversary is able to simultaneously perform signal cancellation at both the receivers. In this example, the D1 is transmitting a signal which is received by D2 and A, and adversary can perform the cancellation. Now we extend this to a three receiver scenario. The adversary to perform a simultaneous cancellation of D1 signal at D2, D3, and A will have to be placed at the intersection point of these three ellipses. But geometry tells us that no such intersection point exists when D1 is the common focal point of these ellipses, so this attack becomes impossible. And to verify this fact, we performed experimental evaluations using USRPs. And since no intersection point exists, we placed the adversary at candidate points which are close to the intersection, which can be close to the intersection points or the intersection points of two ellipses. And in this plot, we see the cancellation probability against the different location for both scenarios of one transmitter to three receiver and three transmitter to one receiver. And the cancellation and the detection threshold for onslaught is set to -50 dBm. And from this figure, we can see the cancellation probability is always less than 10 to the power -4. And there are two important points that we deduct from this experiment. That first, since the wavelength is so small in centimeters, so a little bit perturbation from the perfect point will lead to significant degradation of the capability of adversary to perform the signal cancellation attack. And we use this property to build a secure pairing protocol. And in particular, we use this property to provide the message integrity verification during the message exchange for this pairing protocol. So in this example, in this setting of group, in this example, suppose D1 transmits a message M1 which is received by D2, D3, and A. And M1 can be a DH public primitive. And sequentially, D2 transmits a message with M2, which is received by D1, D3, and A, and which is followed by D3 and A to transmit their messages. And after this message exchange phase, D1, D2, D3 will have the exactly same message, the protocol transcript, and which they will use during the integrity verification phase, where they will simultaneously transmit the hash of the protocol transcript S. Since this transcript is same everywhere, so all the on-slots and off-slots here will be aligned. So now let's see how an attacker can attempt to hijack the transmission of M1 from D1. So the attacker can easily inject its own message MM by using overshadowing attack, such that MM is received by D2, D3, and A, while D1 still has its own message M1. So now after the message exchange phase is complete, D2, D3, and A will have a different protocol transcript SM, whereas D1 will have the correct protocol transcript S. So now during the message integrity verification phase, when the hash of SM and hash of SS are transmitted, to pass this verification, M will have to perform signal cancellation at D2, D3, and A simultaneously. But from the previous slides, we see this is only possible at two locations. So it will be able to cancel only a D2, D and A, whereas D3 will detect the difference in bits of hash of SM and hash of S. And after this detection, it will raise an alarm where it will switch from transmitting the hash to transmitting all onslaught to corrupt the transmission from other devices. And this will be received by D2, D1, and A, and which will in sequence start transmitting this error message. So so now we can see how we can use the classical Diffie-Hellman key and provide the message integrity verification using words. So here each device can transmit their own key primitive sequentially, and each device and the hub, they will compile the transmission transcripts. And after verifying the number of participating device, A will synchronize all the devices, and they will transmit synchronously the hash of the transcript in on-off keying. And during this transmission, each party will verify that there is no energy during off slot. And after this, they will generate a pairwise key, and further they can generate a group key if required. And finally, concluding this talk, we proposed VERS, a physical integrity verification protocol, which is resistant to advanced signal manipulation attacks such as overshadowing and cancellation attack. VERS can be used to propose an in-band bootstrapping of group of devices which do not share secrets or have advanced interfaces, and the security of VERS is derived from the presence of multiple devices that are used to thwart man-in-the-middle attack over wireless. The security of VERS improves with introduction of more devices as it becomes harder to manipulate signals. Thank you, and I will take questions now.